bear with me. It takes a little bit to get the live stream going on YouTube, about 15 to 30 seconds. But hopefully all of the technical difficulties have been sorted. Okay, let's pause that, get rid of my volume. All right, so we should be running live now on YouTube as well as here on Zoom. So again, I'll just quickly introduce our speaker again. We have Stephen Gallagher joining us from the University of Melbourne, kind of starting off our Schedule B for those of us in the eastern side of the global pandemic here for virtual seminar series. And so a couple housekeeping things again that I'll lead off with. If you do have a question that you would like to ask Stephen at the end of his talk, I would please ask that you type it in to the chat box here in Zoom. I will, if you are attending the live stream on YouTube, I'll do what I can to check that also simultaneously near the end. And then when we have the questions, what I'll do is I will then allow you to either ask it in person, so I'll give you a few seconds to chime in, or I will then read it out for you, and then that's how we'll answer the questions. And so without further ado, we're just gonna get started. So if Stephen, you could share your screen and talk a little bit about monsoons.
Okay. Okay. All right. Let's see if I can get it to show. Okay, here we go. Welcome to the Australian time zone, and I'm going to give you a talk about the Australian monsoon. And
Stephen, your screen's not yet.
Okay, sorry. Okay, hold on. I'm screen sharing. It says. Can you see it?
There we go.
Are we there?
It's perfect now. Thank you.
Okay. And you can't see any of this stuff on the side, I presume?
No. No, we can see the slides on the side. So if you go to maybe presentation.
Minimize that? Oh, presentation mode or minimize it. Okay. All right. So once again, welcome to the Australian time zone, Australian Eastern time zone. I've been asked by Peter Clift and the Monsoon Committee to give you a talk on the Australian monsoon. And part of this work is related to the work that I've been doing with many people on the International Ocean Discovery Program and various expeditions. And I'm going to, first of all, I'm going to talk to you about the modern Australian monsoon and what the definitions associated with the Australian monsoon and how it forms and how it manifests itself in our geographic context. And then I'm going to talk about the proxies that you would use, firstly to determine paleo precipitation, and then secondly, whether that precipitation is actually monsoonal. That's a different thing, that's a seasonality thing. And then I'm going to give you a review on the evidence for the Australian monsoon, starting in the Quaternary. I'll briefly go over the Holocene, which is, there's been a lot of work on the Holocene, and then I'll move into the rest of the Quaternary, and then go back in as far as I can to where the evidence is for the monsoon, back into the Pliocene, possibly the Miocene, maybe not in the Eocene. Okay, let's see what we can do. Let's see now. Oh, what's going on here? Okay, so what's the Australian monsoon? The Australian monsoon controls the rainfall distribution in the northern part of Australia. Huge area in the northern part of Australia. And most of the rainfall occurs in the Austral summer, from December to March, the wet season. Just give you a bit on the background to the Australian monsoon. The Australian monsoon broadly follows the intertropical convergence zone. It's not quite, because the zone can extend further south. So this is this zone of atmospheric convergence, just in about 15 degrees south. Just to give you a bit of also a background to the oceanographic situation, which is relevant. So we have the warm pool here, or West Pacific warm pool. and the Indonesian through flow bringing warm water into the Indian Ocean. This weird Lewin current, warm current down the west coast of Australia. Along the intertropical convergence, we have the East Australian current and warm currents that go down the east coast of Australia and the west coast, and then there's the West Australian current. Now you'll see on this diagram, the summer rain dominates in the northern half of Australia in a kind of a diagonal way from northwest southeast, and then the winter rain or westerly dominated climate dominates the southwest and southeast parts of Australia. So during the Austral summer, heating in northern Australia, the atmospheric pressure reduces, cuts off the trade winds, and you get with northwesterly and westerly winds, and then they just generate a wind stream which is over 3,000 meters thick, and this is what Gentili calls the monsoon proper. Now you'll see there's a bit of terminology in the Australian system. Everybody talks about the Asian monsoon, the Indian monsoon, and so on. We talk about the Australian monsoon, and then there's the Indo-Australian monsoon, which is the monsoon that affects the Indonesian region. Even in Australia, we have our own terminology, according to Gentili. But as far as I'm concerned, in terms of the geological record, it is the Australian monsoon. But nevertheless, Gentili, should be with an I there, suggests that those trade winds in the northwest part of Australia, where you get this deflection, and I'll show you a map of that. So it's not really a monsoon, it's a pseudo monsoon. And on the east side of Australia, northeast side, there's also a deflection from a heat low in Western Queensland. And I'll show you the circulation in that region, and that's called the quasi-monsoon. All right, so what's the manifestation of the monsoon, the Australian monsoon? Very clearly shown here in the cyclones that are reaching as far south actually as 22 degrees south and affecting all of northern Australia. So whatever you call them, quasi-monsoon, pseudo-monsoon, there's definitely seasonal precipitation variability, huge seasonal precipitation variability, which constitutes a monsoon. And here's another higher, larger scale perspective on cyclones in northern Australia. I'll show you a few more of these. Now, so this is what Gentili means by the pseudo-monsoon and the quasi-monsoon. So I'll tell you about these diagrams. This is based on Gentili's atmospheric circulation map, but it's also based on the CMAP monthly precipitation climatology for a couple of decades or more. And so you can see, I've superimposed the circulation, and you can see there's two extremes. There's the dry season in the Austral winter, where all the trade winds trend towards the northwest, and there's virtually no precipitation. And during the wet season, or the monsoonal season, we get the circulation deflecting in the northwest. So it basically, all the circulation reverses, so sensu stricto a monsoon, but you still get the northwest directed trade winds here. And you have this feature, you have the intertropical convergence zone, which is this, which actually goes up here. And then this is called the monsoon shear line. And that's the path of the monsoons as you can track them on northern Australia. And I'll show you a detailed map of that. So clearly this variability will result in different types of geological records, this seasonal variability, but of course it depends on whether you can get annular records or millennial and so on. And most of the records, not surprisingly, are millennial or of eccentricity obliquity scale. So one of the key things about these two systems is that the different geomorphic aspects or parts of Australia react to these, to the monsoon and the dry season. So all these rivers, so the De Grey, Fitzroy, Fortescue, and to a lesser extent Ashburton on the west coast of Australia, are ephemeral monsoon controlled rivers primarily. And then these lakes, Lake Gregory, Lake Woods, which occasionally fills up. And then on the east coast, the Burdekin River and the Fitzroy River, coincidentally, same name on both sides, it also are highly monsoonal in their flow. And then, of course, all of the monsoonal flow from the northern part accumulates into the central part of Australia in the Lake Eyre Basin and at its extreme, Lake Frome at about 30 degrees south. So even these lakes here record the monsoonal activity in Australia. Conversely, the dry season, you get dust transported off northwest Australia with the trade winds, and the desert. These are the deserts that pervade the central part of Australia. All right, so talking about the monsoon shear line, it's basically where tropical cyclones form, and it's the boundary between the easterly trade winds and the westerly. So it's essentially that duality in circulation. And this is McBride's work, and you get monsoon convection, and then you get tropical cyclones, TC here, monsoon depression, and you can see that the cyclones track all the way down to 22 degrees south. And here's one of these cyclones on the west coast of Australia in January 2011. And this is a really spectacular image of 3 cyclones, the Australian monsoon manifesting itself, one in the Southwest Pacific, one over Queensland, and one over Northwest Australia. Substantial precipitation, not surprisingly, and there's potential for substantial plumes and flood plumes in the marine areas across the northern end of Australia, and obviously filling lakes and rivers. Here's another couple of cyclones here. And conversely, in the dry season, this is Cape Range on northwest Australia. This is the dust plume coming off Cape Range. So that's about 22 degrees south. And beautiful dust plumes of the Kimberleys here during the dry season. And so clearly the dust record in any of the marine strata in this region is going to be important. This is, I was astonished with this imagery here. This is the De Grey River on the northwest shelf of northwest area of Australia, and the Fortescue River. And I couldn't have planned it better. We had this IODP expedition, 356, and we drilled these things. And this is a monsoon that happened and caused a plume of siliciclastics onto the shelf, reaching out as far as the outer shelf. And you can see these little fellas here. There's reefs in the northern part of this. I'll go backwards. Let's see if I can go backwards. Can't go backwards. Okay. Okay, I can go backwards. You see those little reefs on the top there? Those reefs are in 400 meters of water. So these siliciclastic plumes reach out beyond the shelf and into the slope, actually. So you can deliver siliciclastics, monsoon siliciclastics, into the deep water via these mechanisms. Okay, so some of the effects of the monsoon. This is the monsoon proper in northern Australia, in Darwin. Very evocative scene here. And this is the pseudo monsoon hitting the Pilbara in northwest Australia. Yeah, it doesn't look that different. And this is the quasi monsoon, which is in far north Queensland. And you'll notice that's in March 2019, and that's in March 2019. So whatever you want to call them, quasi, pseudo, or true, this is the manifestation of the Australian monsoon. And in central Australia, the dry lake air, salt lake air, turns into a vast inland sea, collecting waters from the Australian monsoon. And this is just a nice example of before and after airborne imagery of the Lake Eyre region. All right, so I'm now going to talk a bit about the modern flora and seasonal rainfall, and then I'm going to talk about proxies. And so here we have from Kershaw and Van de Kar a very nice diagram showing you the distribution of the flora. And the true rainforests are up in the equatorial region. There's little patches in Queensland of true rainforest. But most of these northern parts are characterized by woodland, sclerophyll woodland. And then there's this vast area, which is a desert area generally. But there's ephemeral floods in this region, which are important, and that is still within the monsoon zone. And on this map from the Bureau of Meteorology, you can see that this is the zone that we're interested in, the wet summer and dry winter seasonal rainfall over 350 mils per year. All right, this is a complicated diagram, but it's important to set the scene on the controls on the Australian monsoon. So we're talking about the very top, the modern monsoon. And one of the things I've been very curious about is all the boundary conditions that you need to create the Australian monsoon, and how far back do these boundary conditions exist to create this massive precipitation system. All right, so on the left here we have the Paleo Latitude of Australia from 50 million years to present. And I've got this is Thomas Westerhol's really great recent isotope curve with some of the people in the audience there. And so you can see a few things which are important with this Paleo Latitude. So during the Eocene, we were in the high Paleo Latitudes. And as we were moving northwards, eventually we passed the 30-degree Paleo Latitude. And so really, when you look at this diagram, you can see that the 20 is the number. So it looks like, yeah, maybe if you at a push, some parts of Australia got into the tropical influence zone. But in reality, it was only by 20 million years ago that we were actually approaching the zone where you could possibly get the intertropical convergence, or at least we were getting into the tropics. But of course, let me qualify that by saying, of course, the boundary conditions or the atmospheric temperatures have changed, and you have various climate optima that artificially bring subtropical climate conditions further south. And if you look at this diagram, on the right here, this diagram is also adapted from Baumann, who did a really good synthesis of all the factors that control the monsoon. And I put this diagram onto the Westerhol curve and added to it so that you get the context. So when we were in the high Paleo latitudes, we got high CO2 levels, greenhouse conditions, no ice caps. And then you have the onset of the glacial conditions at 34 million, the OI1 glacial. And then there's a step towards the glacial world as you go into the Oligocene and the Miocene. And as you can see with these isotopes, we're basically moving towards the icehouse world more. Now, interestingly, the way it's drawn here, you see that it's a very strange scale. So we have a very big scale here. It's not linear. And so there's 3 million years here, which kind of all condense up here on the top left-hand side. But that's where a lot of the action is happening that is controlling the modern Australian monsoon. And then, yes, certainly by the Oligomycene, we were approaching areas where there was low latitude seasonality. So we actually had potential for the seasonality that would be related to monsoonal effects. You have the uplift of the Tibetan Plateau here. And then by 3 million years, actually things start looking more familiar. You get the 40 kiloyear, the 20 kiloyear to 100 kiloyear cycle worlds. And then this graph of wet dry is the ambient variability. So you have a kind of a wetter Pliocene, and then it dries up and becomes more extreme. And all of that's condensed into this top bit. So the question is the mid-Miocene climatic optimum and the fact that we were down just entering the tropic zone sufficient to have generated what you would call an Australian monsoon? Could there have been an Australian monsoon in the Eocene? well, we'll see what I can dig up. One thing that is clear from the Quaternary is the glacial and interglacial extremes of climate are well known, obviously in the last cycle. And this is from Kershaw and Van der Kaar's really nice map showing how the flora changes between the glacial and today. And you will see that obviously aridity is a major feature of the last glacial maxima and desert dunes, and all the sclerophyll woodlands move northwards. And there's no doubt during this last glacial maximum, the intertropical convergence must have moved northwards in this region here. And then obviously during the interglacials, it's moved southwards and then sometimes inundated, got down as far as 18 degrees south. So, I mean, that's fairly well established, the glacial, last glacial maxima, climate extremes, and Holocene. All right, so how do we determine paleoprecipitation in Australia and indeed everywhere? So you look at the facies, so you get the marine facies, the occurrence of fluvial facies, lacustrine, lake deposits, aeolian sand dune deposits, swamps, coal, peat, the presence of evaporites. And in lots of areas, actually on the northeast side of Australia and the northwest side, you get these alternations of siliciclastic poor and siliciclastic rich sediments in marine core, which are basically proxies for precipitation on land and the plumes that go into the sea. You can date river deposits in ephemeral drainage systems. Very important also to date them properly. It's really quite difficult to date fluvial phases in the arid continental part of Australia. You can try and estimate the height of lake shorelines, say of all these Lake Frome, Lake Eyre, Lake Gregory, and I'll show you some data associated with that. You can estimate the dust flux in marine cores. You can date the sand dunes in Central Australia and desert pavements. You look at the fauna and flora, its biogeography, its distribution, spatially and with time. You look at the geochemistry of the strata. There's a kind of a marine bias to this. That's just my expertise, but anyway, you'll have to humor me. So you can use XRF of data on marine cores to determine the amount of marine input or clay input from land. Use downhole wireline log data, gamma logs, multispectral logs, and one that I hadn't realized until relatively recent, the neodymium cadmium calcium ratio in Ruber, in G. Ruber, planktic foram in marine cores. And of course, you can study speleothems, their growth variability and geochemistry. But of course, there's not that many speleothem studies in the northern part of Australia, but still there are some. So evidence of hyperaridity, here's something we got from Northwest Australia. These are evaporites and anhydrites, nodules, a perfect, what we call SABCA environment. And this is what Northwest Australia looked like 1 million years ago, or 11 million years ago. And that really wasn't a monsoon type environment. And Jeroen published on this, on these sediments from Northwest Australia. And then Beth Christensen looked at the siliciclastic, I'll show you some of the data, but she looked at the siliciclastic input in the northwest part of Australia as a proxy for humidity and precipitation. There are ooids and other calcareous features in these strata, in these marine strata, that can only occur in arid environments. So you get these arid phases and you get the higher precipitation phases, and they're well preserved. Okay, see if I can get this to work. All right, in northeast tropical Australia, Kershaw and Van der Kaar and Moss and co. have studied Ocean Drilling Program Site 820 and Lynch's Crater. And here's a beautiful summary by these authors of the distribution of rainforest angiosperms and gymnosperms. And you can see that clearly there are distinct phases of gym and rainforest taxa, and then you get these sclerophyll trees and shrubs, and you get this alternation of and eucalypts and so on, and that's clearly a high precipitation versus an arid phase. And they do match. If you look on the right hand side, you can see there's MIS5, so that's 100 kiloyears, and then MIS2, the LGM, and then more interestingly, they document the charcoal in the preparations. And as I'll mention, the charcoal can be actually quite important in these records. Possibly not younger than 50,000, because that could be an anthropogenic or human-induced charcoal input. But many of these charcoal peaks are common, and they occur when you get high rainfall forest taxa, and I'll talk about that in a second. Here's some more pollen data from the equatorial region, about 5 degrees south, and then this is a section of Northwest Australia. But once again, wet interglacials, dry towards the glacial stages. And interestingly enough, and these data here, you see there's actually this is an obliquity, or sorry, a precession pattern here, every 20 kiloyear cycle here. You can see there's actually a precession pattern in some of this data, very distinct at the bottom here. So insolation is obviously a strong control on the Australian monsoon, or sorry, on precipitation, should I say. All right, so what are the proxies for the Australian monsoon, i.e. the seasonality? And it's actually not that easy to determine in deep time. You can use palynological data and paleobotanical data and use transfer functions and modern analog techniques to estimate summer and winter precipitation. One of the things I've noted in the data is that you often get charcoal peaks during times of peak rainforest. And so it's possible that they actually denote seasonality. So you must have a dry fire season, and you must have a wet monsoonal season. So my eye was drawn to those patterns in the palynological data. Clearly, those central Australian lakes are monsoonal influence. There's no other thing that's going to fill them up. Obviously, if you get too far south, you're going to get the southwesterlies. But nevertheless, those monsoonal lakes are very important. Another way of getting annular records of the Australian monsoon is coral luminescent layering. And people have used that in northeast Australia in the Great Barrier Reef to get the intensity of basically interannular monsoon variability. So you get these organic layers during the monsoon, and then you get this annular beautiful banding in Porites coral. And then there's organic geochemistry proxies, C4 and C3 plants, and their relative abundance has been used certainly on the northwest shelf of Australia to add to the evidence of the existence of a strong monsoon. So just give you an idea of some of the data, not much data, but Sander van der Kar, who's a really good palynologist, also did transfer functions and estimated, this is a site on northwest Australia, which is at 22 degrees south. And you can see here, this is from 100,000 to present. There's a gap here. You can see there's mean summer rainfall, high mean summer rainfall during certain periods, and then low mean summer rainfall. So arguably that's the monsoon. Arguably the peaks here represent the Australian monsoon where you have peak summer rainfall. And so the kind of data that I've reviewed there, I've incorporated into a series of, I hope you'll bear with me, these are quite complicated looking diagrams, but they have a theme to them, okay? Uh-oh, here we go. Right. All right, so let's get your bearings on this one. So I've taken the east side of Australia and I've looked at a latitudinal transect. So this is a transect of a Marianne Dufresne core, a core from here at 5 degrees south. Then there's another Marion Dufresne core at 9 degrees south. And then there's the classic work by Kershaw and Moss and co, ODP 820, Lynch's crater here. And then Central Australia, there's actually quite a bit of work done on the river deposits and the extent of the lakes and dating of the lakes. And it's actually been quite well. It's actually, Fu here has actually done some fantastic work adding with Cohen to kind of date these lake levels. And so what I've got here at the top here is, this is Liu et al. 2015 using Ruber neodymium calcium ratios. And he surmised that precipitation levels were running in with insulation, basically. So you actually insulation was controlling precipitation and by proxy, the Australian monsoon. Now the floral record from further north here shows the green here is humid, wet conditions shown by the flora. The yellow or kind of light green is our arid conditions shown by the flora. There's this very interesting little blue strip. That's our Sandavandakar's work on transfer functions, and he's estimated summer precipitation. So what I've done is I've superimposed his peaks of summer precipitation. So one thing that you can get from, and also on the top here, I'll just go back. I just keep touching, yeah. On the top here, we have the charcoal peaks. All right, so on here, the charcoal peaks, definitely in this period, down in the 100,000 year range, are coinciding with high precipitation. So this is probably indicating monsoonal rainfall. Interestingly, the work by Sandavandakar doesn't give you summer precipitation until here. But the key thing with this, and I can't emphasize enough, is that there, according to Sandavandakar, there's high summer rain precipitation during the last glacial maxima, which means the intertropical convergence zone was in this area. And even though it was drier, I'll just see, go back. Yeah, even though it was drier during the last glacial maxima, the intertropical convergence zone was over PNG or in this region. However, when you go down to, unfortunately, there's none of these proxy records from transfer functions down here, but you see that there's a general wetter period in the ODP site 820, Lynch's crater, all during stage 5, stage 4, to some extent in stage 3. And then there's these arid phases. And we have little peaks of charcoal during these times. And of course, humans arrive in Australia about 50,000 years ago. Some of these peaks may be human-induced, and during the dry periods, you would expect high fire periods anyway. But nevertheless, there's kind of a general sense that you have high rainfall during the interglacial stages, and drier periods towards the glacials. It's the same here. Once you get to Central Australia, these are Nansen and co-authors have dated river deposits all around this region in the Lake Eyre region. And the dark green is the most intense or the most common river deposits. And then there's less common. And so all of these proxies are stacking up in the wetter stage 5, wetter stage 4. And then you move down into the Lake Eyre basin, and you've got Fu et al. And Cohen have dated Lake Frome and Lake Eyre shorelines, and quite well constrained actually. And arguably that's an insulation variability there in the monsoon. But nevertheless, you see that there's no doubt, and I forgot to mention this Holocene data, of course, from various areas, but not in this region. But there's no doubt that the monsoon is more intense in the stage 5 and stage 4. And so you could argue that the quasi-monsoon is actually existing during this time. And it basically, it's only, and it kind of basically shuts off or gets less intense. And the monsoon belt just moves northwards during the glacial periods to the equatorial region. All right, what about the northwest region? Northwest Shelf. Actually, I'll jump down to 22 degrees south, which is the Cape Range region, which is at the extreme of the pseudo-monsoon, the Australian pseudo-monsoon. But luckily for us, our friend Sander van der Kar has actually done some palynological work for this last 100,000, which I showed you. And you can actually see that the summer precipitation here is very distinct during this time. So the rainforest proxy from the Flora and the precipitation index points to a summer monsoon during definitely stage 5 and 4. Okay, jumping back to the very north at 13 degrees south, and there's other records from other IODP sites which are hopefully coming. But here we have a record that has a wet stage 5, 4, 3, and then a dry glacials. Yep. And then we have charcoal peaks at various times. So this is the monsoon. And then Lake Woods, which is a monsoon lake here, and Lake Gregory, which is here, both worked by Bowler and McGee and so on. They have these little patches of high lake levels during stage 5 and to a lesser extent during stage 3. Now, the problem with those this lake work is it's not very well constrained chronostratigraphically, but these other sites are well constrained, the MD98, 2167 and so on. And then moving on to ODP sites 762, which is Stutz's work. He's done a lot of XRF scanning, and this is the log of iron calcium, which is a proxy for siliciclastic input. And as you can see, the peaks of iron calcium are corresponding, or I've interpreted them as wet phases, and they're not too dissimilar to the floral record further north, and then this dry period. So in a gross sense, if you would take this pattern from both areas, you would argue that the Australian monsoon was more intense during stage 5 and 4, became less intense in stage 3, and moved further north during stage 2. So these records are quite important because as you drop back into deeper time, you really don't get the nuance that you have here in the late Quaternary or the late Pleistocene, mid-Pleistocene, to get some of that seasonality or even some of those signals, as we will see. Another zigzaggy, horrible diagram, but it may look like there's a lot of data. Let me go back, okay. It may look like there's a lot of data here, but actually, no. So what I've done here is I've put this little gray area at the top here is that 150,000, where a huge amount of work has been done on the Australian monsoon. And I'll focus you onto this area here, and you'll see once you get to beyond about 300,000, all the lake records basically disappear, or at least nobody's been able to date lake records beyond that, and the rivers and so on. So you lose that kind of very easy to understand Australian monsoon signal, unfortunately. It could be to do with preservation style, or it could be to do with a lot of people are very interested in the Quaternary as opposed to any other time, certainly the late Quaternary. Anyway, looking at the ODP site 820, the only time you can get beyond that, there is a bit of some records that go to 210,000, Peter Kershaw and co. And then you get this very sparse Paleo record back to 1.8 million. That's a bit of a shame because there's so much core up there. This ODP site has some fantastic core that is just ripe for palynological analysis. I'll just see if I can get that to stop going across here. Oops. All right, so let's look at the northwest margin. Once again, we don't have many, so you lose all the proxies, and all you're left with is precipitation proxies. However, as I would argue that the Australian monsoon is more intense in the interglacial periods, or at least the ICTZ and the pseudo monsoon and the monsoon shear line is present there, then on a broad brush, you could say the siliciclastic pulses on the northwest shelf certainly are reflecting increased or stronger monsoon strength or the presence of the monsoon. And if you look at these data, this is just gamma log data, downhole clay versus no clay data from oil industry wells here. This is XRF data from Stute, reworked by Auer and co. And you can, no matter what you can see, you can see this basically a step in aridity in the data. Even actually in the Queensland data, you can see that there's more rainforest taxa and less as you go through time. So there's definitely a step up to increased aridity through time reflected in these data. And there's possibly an insulation control on some of these big precipitation peaks, but I haven't burrowed down into the that data. Now going back even further in time, this is a period gone from 6 million to 2 million, so I've moved my way back. There's even less data for the Australian monsoon century stricto or pseudo monsoon. There's virtually none from the northeast margin of Australia. We are now we're having to focus on IODP Expedition 356 and hopefully 363 in the future. But certainly there's data on the northwest region, northwest part of Australia that point to a step increase in summer monsoon. So let's go through this. So here's the Liseckian rainbow curve, and this is the 3.5 triggered towards the Northern Hemisphere glaciation and kind of the step towards the 100 kiloyear cycles. This is Andre's work on C4 plants in the geochemical data, and the abundance of these things increases markedly at this time. And it does fluctuate a bit, but certainly there's a big step in C4 plant expansion. So obviously the flora has changed to some sort of open mosaic, monsoon floral mosaic, and that's what Andre argued is the case. And so sea surface temperature decreases at site 763, which is just offshore from the coastline there. And then 762, this is the iron calcium ratio, and these are Stute's comments. So you have more aridity and rainfall variability and big changes in precipitation and increases in long rainfall events. So this is to be this, and then this is data from Expedition 356, which is a proxy for fluvial input and precipitation. So we have a wet period, but not necessarily seasonal. I don't think we can discern the seasonal signal in these data, but certainly there's a big step in towards aridity, and that is definitely a drying, and the variability is showing itself here. And so basically what these data would suggest is that if we're looking at a modern analog, the pseudo monsoon of Northwest Australia really started about 3.5 million years ago. So how far back? So actually, I did show you some data from one of those anhydrites from, that was site U1463, which is at about 18 degrees south. And those anhydrites were down here in 11 million. So there was no monsoon. It was hyper arid during that period. So is there a Miocene monsoon? Those of you who inhabit the Miocene world would be familiar with Harold's work and his modeling using sparse botanical data from Australia, and then modeling it using various thresholds. And he seems to think, or these authors seem to think that, yeah, it's possible we had a early to middle Miocene monsoon, but it was weaker. The thresholds were there for precipitation. There was a high enough precipitation. So, but he's talking about an area which is, 20 degrees south here. So another way of tackling whether we have a monsoon, of course, is by modeling the data that you have and using various boundary conditions. But in my opinion, there's no substitute for data, I have to say. All right, so there's actually a little bit of data from Lightning Ridge, which is in New South Wales at 30 degrees south, which there's these Fabaceae things, with kind of some sort of pea-like plant. And this plant, whoops, go back. This plant, I'll just close this thing. This plant reflects a monsoonal climate. In fact, these Fabaceae are common in monsoonal Northwest Australia or monsoonal Australia. And so Carpenter and co. suggest that even at, this is 30 degrees south today. So in the Miocene, it would have been about 38 degrees south. So even at 38 degrees south, there's a possibility that there was an Australian monsoon and you had seasonality. I just go through. How far back can we go? This is another, as you know, quite famous modeling paper and trying to model the Eocene monsoon. And a byproduct of this modeling suggests really didn't produce a monsoonal precipitation effect in Australia in whatever scenarios. But there is evidence potentially of seasonality from the Flora record reported by Dave Greenwood from Central Australia. So it's kind of equivocal, even though, yes, the boundary conditions were, the CO2 levels were substantial, and we did have big actually coal swamps accumulate in southern Australia during this time. The evidence for a monsoon is not really there. All right, so going backwards to the start. So where's our Australian monsoon record? Well, it is constrained in time and space. So spatially, it's only when Australia moved into the tropical zone where we could get the proper interaction with the monsoon atmospheric systems. Also, you have to have created that Pilbara high and all that circulation. You have to created that alternation. And I don't know whether anybody's actually modeled that kind of scenario, but I can't imagine that that kind of scenario would have existed way beyond 20 million. But certainly there's kind of some sort of evidence of monsoon in the Miocene. Not really, there's kind of a step in the record which needs to be infilled for the post mid-Miocene monsoon record. The strongest modern Australian monsoon, as I said, is down up here in about 3 million. And I don't really think that the Eocene monsoon is sustainable unless we could find some other evidence. So where to next? Well, there's future work ongoing and that has been completed on what could be called the Monsoon Transect. And this is the Monsoon Transect of Western Australia. And this is work by Anne Holborn and Yair Rosenthal on IODP Expedition 363 and 356 by myself and others, has a perfect opportunity to study the, it's essentially a Miocene to recent Paleo Latitude transect, as you can see here. That's the same Paleo Latitude diagram. And it's a perfect transect to study the interaction, the geographic interaction through different optima, climate optima, etc., as Australia is moving northwards, and how it actually, how the modern Australian monsoon eventuated. And of course, Expedition 363 has the perfect records for the monsoon, certainly the Indo-Australian monsoon, but there are two nice sites here off Northwest Australia that are perfect for the Australian pseudo-monsoon. And I'm hoping to see that data, those results come out. And this is just the Expedition 356, and the monsoon, the extent, the extreme of monsoon is just here at Cape Range. So that record I showed you, which clearly showed monsoonal seasonal rainfall according to Sound of Antikythera, was here, just off here, GC 17. So we do have a nice transect, and one thing I hope somebody will do is actually study the flora of these sections and the ones further north, in addition to the XRF data, to try and get this seasonal monsoon flavor out of this. There has been a bit of work. Wolfgang Kuhnt, who's in the audience there, has published stuff from the Australian monsoon and the Holocene. This is a slightly later paper that kind of confirms the onset of the Australian monsoon in the last about, I think it was 12,000 years. There's a whole pile of classic work that's been carried out on that is related to the monsoon that can be studied in all these sites in IODP Expedition 356. And then this is work that Anne Holborn and co are studying fantastic resolution of XRF data and isotope calibration of a section from Northwest Australia. So I'm really looking forward to seeing the results of the Australian monsoon for 10 million years in that one. And really that's all I have to say for now. And are there any questions? Shall I stop sharing?
Great, thank you so much, Stephen. Yeah, so if you have a question, please type it into the chat box, and then we can call on you to, again, ask the question. The chat box is just to make sure that everybody can see and hear the question. So please type away. I'll give everyone a moment here. Those are some phenomenal figures, by the way.
Thank you.
Yeah, it really summarizes a lot of the work that you've been doing. Many others have been doing on the Australian monsoon. All right. Well, as people are still typing their questions.
Oh, there's a question on the Australian monsoon, how it differs from the Indian monsoon. Well, the key difference is the topographic effect. There's no topographic effect on the Australian monsoon. And it has been argued by Virol and co that it actually is therefore controlled by insolation. And there are kind of signals of the insolation variability in the precipitation in the geological record. So it's that plus how the ICTZ behaves spatially through time, and how would we detect this monsoon shear line, which is not the ICTZ, it's actually an extension of that system. How exactly you would do that is kind of not clear, except for it to say that it must be the rainfall fluxes or the stochastic pulses that you get into the marine environment that are recording these paleo cyclones, if you may. So, yeah, does that help? This is from Prof. A.K. Gupta. Yeah.
Ah.
Any further questions?
Yes. Wait a moment.
It's either too late or too early, or just quite right for everybody.
So one thing that I was curious about is if you have a lot of evidence for extreme cyclone activity related potentially to some of this like the strength of the monsoon in your records at all. Has anybody explored that?
Well, I mean, as I say, the picture of that plume on the northwest shelf, and there actually are plumes on the northeast shelf of Queensland that go into the lagoon behind the Great Barrier Reef. So when you see something like that, and you go, well, the siliciclastic pulses that you get, the clay that comes out of that. I didn't mention, but of course the mineralogy of that clay has been studied. People have studied the sources of the clay in the rivers, and Holborn, Jingjal, and all these guys. And so basically these clay pulses must relate to, especially as geographically, for example, if you're at 22 degrees south, the only source of the rain at 22 degrees south, going back 1 million or 2 years, would be those cyclones, really. Yeah. So, I mean, so kind of, you won't get the it'll all get aggregated, and so you won't, because it's in the marine realm, what will happen is all the little critters will often burrow their way through it, and you won't get like little events in the event records, unfortunately. But the chances are that that's just an averaged pile of cyclones that occur seasonally over, thousands of years during the interglacial phases. So yeah, you're right. The concept of fossil cyclones is nice, but really, the geological record is not conducive to preserving that, and compaction, of course, does also perturbation, compaction, diagenesis will kind of iron out some of the submillennial or even, that kind of record would disappear in the marine realm.
Yeah. It's kind of refreshing to hear that, not everything that you're looking at is all extreme event driven, which I know can sometimes be the case or is often the question when dealing with some other records, like especially terrestrial records in some cases. So it's really cool to see that you have so much material and there's just so much that you can do and you're looking to do, you and your colleagues.
Mm-hmm.
Okay, do we have any last questions for Stephen here?
Oh, another thing is that, yes, there's lake deposits in Australia and you immediately think, is there some sort of annular layering that you could get in these lake deposits? Mm-hmm. But of course, the extreme nature of the environment and during these ephemeral lake events, the critters would be going crazy in that, and you wouldn't get varve-like, obviously, deposits in that. In other words, annular deposits in these lakes, because it would all be homogenized in some way, and then compacted, and then of course, most of the time it's super arid, and then all the organic stuff disappears, and it just kills off any chances of studying some of the more kind of exciting wet organic material in those. So it's just, Australia is a challenging area to study the monsoon. You have to go offshore, really.
Okay, well, let's again thank Stephen for his very excellent talk on the Australian monsoon. We will be getting more talks from Australian researchers about the monsoon in future dates, some of which are in attendance here today. So I just wanted to point your attention to the buttons down below the screen. You can give Stephen like a thumbs up or a clapping of the hands. So you can do that into the chat if you like. And so while you might be doing that, I'll just remind all of you that next week on the 27th of January, so also a Wednesday, is the Schedule A seminar with Majia Fan from UT Arlington, giving our talk next week. And I would also like to remind you all that if you are interested in giving your own talk, or if you know some intrepid postdocs or PhD students that would be looking to give a talk, we are welcoming people volunteering for that, and we'll kind of make up a queue and see what we can do with that into the future. But otherwise, please put your email in the chat or send me an email or any of the co-hosts an email, so Liviu or Peter, if you'd like to join kind of an email server that will kind of send announcements related to this seminar. And I think we've got maybe a question actually popping up here in the chat.
Okay, let's see now, the rhythm of Australian monsoon is, governed by orbital parameters, insolation in all likelihood. In terms of tectonism, obviously Australia has moved forth into PNG, and within a couple of million years, we'll be merged in with PNG and high and dry. And so obviously we will move fully into the more constant ICTZ zone. And but then who would worry about 2 million years in the future? However, obviously the anthropogenic climate change aspect and the nature of the monsoon needs to be investigated. And people have modeled kind of what I would call short term, but it might be 1,000 years kind of effects on the monsoon and climate change. But that's beyond the scope of this talk. It's also beyond the remit of the kind of work that we do, given its time zone. But I mean, this is what you've seen here. I'm going to synthesize into a paper, which I hope Peter Cliff will extend the deadline for, I might add. But nevertheless, I want to synthesize what I've got here into a summary paper. And one of the things I'm going to do is I'm going to look at what people have done for the future monsoon, the effect of the Australian monsoon, or what the monsoon might do in the future and how people have viewed that. But however, I'm going to steer away from like annular variations in the monsoon and the dipole type work, because the geologic record is so huge. That would be a massive paper. So, but definitely, I mean, in the first instance, you would expect cyclone intensity to increase with anthropogenic warming, and that's fairly well established as far as I can see. And therefore, the Australian monsoon should become more intense with anthropogenic warming.
Okay. All right. Thank you again, Stephen. And so I guess this will conclude the first Schedule B seminar for the Monsoon Seminar Series. And so I'd like to thank you again all for attending, and I hope you have a lovely rest of your day, and make sure to mark your calendars for next week, Schedule A, for those of you who are awake, or just catch it the next day on YouTube as well. So, all right. Thank you so much. Have a nice night.
All right. See ya. Bye.